Hi folks, Matthew Lanigan here with Baywa RE. We're just going to give it another minute or two for people to log in and we'll be right back with you all in APS. Thanks so much. Hi folks, Matthew Lanigan here again with Baywa RE. I'm the Chief Commercial Officer here at Baywa. Really appreciate you taking some time to learn a little bit more with our friends here at APsystems. Before we get going, just a couple of housekeeping notes. We will be taking questions. You'll notice down in the bottom right corner there is a box, so please, as you have questions, type them in. We'll do our best to answer them as we go, and then we'll also answer them during breaks. This will be recorded. It's going to be on our YouTube channel. If you haven't signed up for our YouTube channel yet, we would love it if you did. You can see this webinar as well as all the past webinars. And also, if you haven't signed up and aren't using our industry-leading web shop yet, we'd really love it if you could. It's a very powerful tool. You can see all the specs, install manuals, inventory, your invoices are all in there. Very powerful tool. So if you're not using that, we'd like to encourage you to have a look at that as well. Continuing education is a very important thing here at Baywa, so we're happy to extend that today here with you. So without further ado, we have Chris Ling here with APsystems, Applications Engineer Manager. Chris?
Thank you for the introduction, Matthew. Give me a couple seconds to share my screen. Okay. Just as confirmation, people are able to see my presentation now. Okay, great. Thank you for confirmation. Cool. All right. So, welcome everyone to this webinar on how to master the QT2. My name is Christopher Ling, so I just go by Chris, fewer syllables. I really appreciate taking the time to go over this product. First things first, I'll just go over some boring information about our company. But basically, I just want to reiterate that we've been strong partners with Baywa for many years, and we also have a pretty large global footprint all over the world. Our headquarters is based in Jiaxing, China, which is a little bit close to Shanghai, but not in Shanghai. We also have various business units within Canada, of course, within Europe, the United States, Mexico, Brazil, and Australia. As mentioned earlier, we have a pretty extended history with regards to making multi-module module level power electronics. Our company was founded in 2010 in Jiaxing, China, and then we have expanded ever since. And actually, the really fun news I'd like to report is that we recently hit our 15-year year anniversary. I think it was around last month. So the companies we've been around for 15 years, and our hope is that we continue to be around for 15 years more. Probably, hopefully more than that, of course. Just as a brief overview, if you're familiar with APsystems, this is our bread and butter, which is the APsystems residential solution. This is not the focus of this webinar, but I will just briefly mention that we have the residential microinverter. So it's 2 panels into 1 microinverter. In terms of the architecture, the way it works is that we have the microinverters. They're the devices that produce the power. We have an ECU, which is the gateway device that communicates to the microinverters and collects data from the microinverters. And then it sends data into the cloud. And the cloud data is accessible by our EMA online monitoring platform. Now, this is what we're here for today, which is the commercial solution. So remarkably, the architecture is very similar, where the ECU is basically the same. We have a commercial version if you want to have additional functionality. The EMA platform is also the same as well, but the more exciting part is going to be the QT2, which is what we call the microinverter for commercial solutions. So the architecture, once again, is very similar from the residential microinverter solutions versus the commercial one. So in any case, that's going to be the main topic of today's webinar, which is going to be how to master the QT2. So first, let's define, let's talk about what the QT2 is. So the naming convention of this microinverter is Q stands for quad or 4 input. So this refers that you can put 4 panels into a QT2. It is also 3-phase. So the nice thing about this inverter is that it's native 3-phase. So normally with a single-phase inverter, you have to put inverters into different branches and then make sure that each line or each branch is properly balanced. But in this case, this microinverter on its own outputs 3-phase. So you don't need to do any sort of like branch management, making sure each branch goes to 1 phase. So that is not necessary for this. 2 is referring to our 2nd generation. For those who are familiar with our YC1000s, that's our first generation. I guess back then we didn't call it QT1, but if we were to go back in time, we would call that a QT1. But then in this case here, we have the QT2, which is our 2nd generation. Why is it 2nd generation? Main things is that it's higher output compared to our YC1000s. The 1000 refers to I believe it's the AC output, but in this case here, we have 2 flavors of the QT2. We have the 208 volt and the 480 volt. The 480 volt can do 1800 watts output. The 208 is a little bit less. And that basically corresponds to 450 watts per channel for the QT2 480s. The quick number that I like to say is that if you want to achieve a 1.25 clipping ratio, you can put 550 watt panels onto each channel. So to summarize, if you want to get a 1.25 clipping ratio with the QT2s, you can do 4 550 watt panels onto the microinverter. So that's quite powerful. It's possible to use higher wattage panels. That's okay. Just the main thing is that your AC output is going to be limited. You'll get a little bit more clipping, but sometimes that might be more favorable depending on the situations. As mentioned earlier, it's a native 3-phase, so it outputs L1, L2, and L3. And if people are curious, it pushes power on the line-to-line, on the line-to-line outputs, as opposed to line to neutral. And it also has all the necessary certifications, in particular UL 1741 SB. So it has so it's able to meet those requirements. And of course, because this is a micro inverter, it's rapid shutdown compliant. Oh, probably different in Canada, but those are the main selling points of the QT2. Any particular, I'll leave a quick pause for here if there's any questions. If not, I'll go more into the architecture decisions as to why you would use commercial microinverters, because I think a lot of people are thinking, why would you ever do something like this since it's such an expensive way to do commercial?
Hi, Chris, we do have one question. Is it a different SKU for the 208 volt or the 480 volt, or can I do either voltage with the same model?
Oh, it's a different SKU. So there's a different part number for each of the microinverters. Thank you for the question. Okay.
Great,
All right.
thank you.
So no, absolutely no. Thank you, Matthew. And thank you for the question. Once again, I really appreciate the questions that people are asking. So first off, I'll start high level and I'll give a little bit of explanation as to why we want to go for commercial microinverters, why you would want to use a commercial microinverter, because as mentioned earlier, it's not the answer for every case, but there are some scenarios where a commercial microinverter could be helpful. So first of all, a microinverter is a true low voltage system. If you have a if you have a string inverter, there is a risk of having high voltage DC on the roof. And with my American colleagues, a lot of people are sort of having questions with regarding to having module level rapid shutdown devices. And now they're even thinking, and there's now also conversations about there being a new UL certification allowing you to not require module level shutdown for panels. So one thing I will note is that if there's a scenario where you absolutely cannot tolerate like high risk arcing events, then a microinverter is going to be very useful for those scenarios. Because when you have string systems, you will have the possibility of having high voltage, and with high voltage comes the risk of arcs. But with a true microinverter solution, the maximum voltage that you can actually the maximum voltage that you can get from a DC side is just going to be one panel. This image actually I need to have it updated. It should be below 60 volts as opposed to 120 because we have some microinverters where you can put two panels in series to get you 120 volts, but that's not. But we don't sell that in Canada because I don't believe it passes a certification in Canada. But in any case, for microinverter solutions, the maximum DC voltage you'll even potentially get is a single panel. So if there's scenarios where you absolutely need to make sure that is a safe system and you don't have any arcing, high voltage arcing whatsoever, then a microinverter is useful for that, for like churches or schools or something where insurance can be very expensive, you know. Another part also is inverter failure impact. So for string inverters, if a string fails, the worst that can happen is the entire string goes down. But for a microinverter, the worst thing that can happen is four panels go down. It is possible for the inverter to fail where like one or two channels fail, so the impact is also smaller from that perspective. But this allows you to get a little bit more flexibility and leeway with regards to being able to fix the system immediately. Another useful feature as well is you get module level monitoring as well. Once again, this is not always necessary for every customer, but if you need to know like module level information, like which panels are underproducing or which panels are having problems, or even like which branches are having issues, you can get all that information from here. So you get DC level voltage and currents for the micros, and you get AC level information for each of the microinverters as well. So as mentioned before, there is definitely a little bit of premium just from a BOM perspective when you have a large number of panels. So for me in general, I generally like to recommend the QT2 for mid-sized commercial projects where safety is critical and paramount. And if you need and if the how to say single point of failure is something that's uncomfortable, then a microinverter solution will be able to solve that. And the module level monitoring is also important to a customer. This is something that they can offer as well. All right. So in any case, that's a high level discussion on making the case for commercial microinverters. Any questions? Otherwise, the next topic, I'll talk a little bit more about the hardware and the cabling of the system.
Any questions out there, folks? I don't see any at the moment, so I think we're good to go.
Okay, cool. Sounds good. All right. So first things, I'll talk a little bit of how the accessories work. And this is basically how the layout goes. For those who are familiar with our DS3's microinverters, this is actually remarkably similar. So let me pull up my laser pointer. Okay, so at the top you can see here that this is the trunk cable, and that's where all the microinverters are plugged into here. And we have an end cap on one side to basically cover the wires to prevent any shorting on that side, and this basically goes on the other side, goes either to a J box, or you could use an AC connector to like run it to an AC combiner down below. And we also have caps that if you want to skip a drop, you can skip that. And then for microinverters, you don't have to use all 4 channels. It's actually possible to just use 3. It's not as the most efficient from a like cost perspective, but if there's like if there's a multiple of not 4 micro panels, you will need to waterproof the DC connectors with the caps so that they're unused. And then we also provide a DC extension cable. So if you have panels that are a little bit further out, you'll be able to use those cables. One thing I will let's see. One thing I'll also mention is just in general, don't hold on to the microinverters like a dead chicken on the AC cable because it strains the gland. One of our tech support agents, she said that these inverters kind of look like purses. So you ideally want to hold them by the handle of the purse. I don't know if you want to use that metaphor, but that's one way to think about it. And once again, from a wiring perspective, this is how it works. I will mention, actually, I realized that this diagram is not up to date. It should be 5 pins as opposed to 3 pins. And from a wiring perspective, the wires are L1, L2, L3. And in the trunk cable, we have neutral and ground. I will note that it is actually possible. It's actually okay if you're using your home run to not to just use 3 wires and to not connect neutral and ground unless it's necessary from a code perspective that you need to run neutral. But neutral is not necessary for for the system to provide power. Ground is also not necessary because usually you're grounding from the rail, so you don't need to use the bus cable for grounding. But the main thing is that the important wires to connect is L1, L2, and L3 for the 3-phase output. And just from a number of microinverters per circuit breaker, because the trunk cable is 10 gauge, you're going to be using 30 amp breakers. If you're using 208, oh man, there's a typo I need to fix. So if you're using 208s, because the voltage is lower, current is going to be higher. So you can only put a fewer number of micros, so it's going to be 5 per 30 amp breaker. And if you have the 480s, it's going to be 11 per 30 amp breaker. All right. I'll briefly talk a little bit about the mounting of the QT2. It basically looks something like this. Main thing that we ask is that the QT2 is going to be covered by the panel. So if it's like sort of sticking out underneath the panel, or if it's underneath the panel and there's like a little bit of like a gap in between the 2 panels, that's not ideal. So the important thing is to make sure that it's completely under a panel, and it's also okay if it's at a different angle. And the main thing is just making sure it's under a panel here. Typically, it's basically mounted through MLPE mounts. These inverters, the QT2s have 2 of them, so it's easy to mount them like so. So as mentioned before, make sure it's not exposed to direct sunlight, and make sure that there's sufficient spacing between the microinverters and the panels for proper ventilation. As mentioned earlier, from a grounding perspective, there's a grounding washer that ties it to the rail. So the rail is grounded, then you'll be okay. We also have a optional grounding lug. I don't think this is going to be necessary in Canada, but we had some utilities, I think in Europe, where they require you to have an externally grounded connection to the microinverter itself. And so if that's necessary for whatever reason, you can do that, but it's not necessary if you're using the grounding washer and rail grounding method. Okay, any questions regarding the mechanical features of the wiring or mounting of the QT2? If not, I'll talk a little bit about our design tool.
Not seeing anything at the moment. We're good.
All right, cool. All right, next thing I'll talk a little bit about is the AP Designer tool. So main thing is that I don't have time for a demo. But if you have access, if you have an email account, if you go to the top of the screen, there's something that says AP Designer tool, and if you click on that, you'll be able to use that as a way to sort of design your systems. So given a layout, you can place your microinverters, do the AC cabling, and do the DC cabling, and then you'll be able to get a bomb as a result of your systems. Um, I have this sort of diagram that kind of explains the different wiring that you can do with the QT2 layouts. So all these are totally fine. Just remember, just the main thing is that you will also need DC extensions for panels that where the DC whips are not as long and the panels are a little bit farther out. But the AP Designer tool will be able to help you figure out how to do all that information. So the steps are basically you pick the location, put your modules, do the wiring, generates a bomb for you, and you can even also, if you provide additional information, it can let you know production value or expected production values based off of the angles and things like that. Okay, cool. So that's the AP Designer tool. The next topic I'll be going over is going to be the ECU communication gateway. So I'll move on to that. All right, so the ECU is the gateway device. So as mentioned earlier, it serves as first it collects data from the microinverters. So any production, any error alarms is collected from the micros. It's also responsible for pushing any sort of remote control or updates. The gateway is also responsible for as well. And this gateway device is also connected to the internet as well. So it can be either connected via a Wi-Fi connection or an Ethernet connection. And overall, it looks something that looks like this. So the ECU talks to the micros via Zigbee. And Zigbee is the wireless communication that the microinverters will be talking to the ECU with. And to talk a little bit more, it looks something like it looks like this. So the rule of thumb that we usually give for Zigbee is that first of all, it's a mesh network. So the microinverters sort of talk to each other and pass data along into the ECU. And in general, we say like 75 microinverters per ECU. It's not a hard limit. So it is possible to put a little bit more microinverters than 75, but it's possible that the latency of the data increases. So you start getting so data might be slightly slower with more traffic. In terms of range, we typically say 75 meters or 250 feet maximum, but that's usually for like an open field. But I'll talk a little bit more about the limitations of, or not limitations, but the considerations with regards to ECU placement. The device that I have shown right now is called the ECU-R, and that's basically a more how to say the simpler version of the ECU. We do have another flavor of the ECU called the ECU-C. It's the same as the ECU-R in terms of functionality, but the key thing is that it has port places where you can put current transformers onto them, and that allows you to do consumption monitoring, CT measurements, and for export control. It's not necessary for every project, but if you notice that there's a requirement where that you need to have that sort of monitoring information, that's the way to go. Um, and then from a wiring perspective, the important thing is that from a power that you power the system directly through the wires in here. And main thing is that if it's three phase, make sure that you plug in L1, L2, L3 neutral and ground. If it's single phase, that you just have L1 neutral and ground. If it's split phase, you want to have L1, L2 neutral and ground connected. Okay. I'll pause here. My next topic is going to be going over ECU placement. But are there any questions with regards to the ECC and the ECUR?
Not seeing anything at the moment. I think we're still good.
Sure. Let's carry on. So, given the 75 microinverter limit, if you have a much larger system, there's going to be scenarios where you're going to need to have multiple ECUs. So I will talk a little bit about how to handle a multiple ECU layout, and I'll also talk a little bit more about like how to think about ECU placement. Because as mentioned earlier, it's a mesh network, and there's limitations from a wireless perspective. So I'll talk a little bit more about that in detail. So first of all, if you have a multiple ECU setup, the important thing is to do the ECU setup sequentially. Basically, what I would recommend doing is first set up an ECU, claim the microinverters through that first, let it form its network, and then move on to the next ECU. So that way there is less ambiguity with regards to forming the Zigbee network. So number one is make sure that we install them sequentially. The second thing is also that the ECU ideally needs to be close to the array that the microinverters are associated with. So in this example over here, this is, I would say, an extreme example. But this ECU, this black one, is associated with these micros, and this ECU is associated with these micros. The way that they're currently placed is not ideal because it's not close to the array that they're close to. So it's better to make them closer in this sort of a fashion. But of course, the better way is to put it in the middle of the array. So that basically allows you to have the best signal strength with regards to the micros. So once again, if you have a multiple microinverter, multiple ECU install, the first instinct is to put both ECUs close to each other, when in reality you actually want them to be separate, like in this sort of a fashion. Third consideration is to make sure that the ECUs are properly sorted out. So if you mix the inverters to different ECUs, that's actually not the right way to think about it. It's the way I would think about it is that each ECU is sort of responsible for its own array. So it's better to have this sort of a configuration between the ECU and the microinverters, so that it's clear on which array is associated with which ECU. Another configuration as well is to be cognizant with regards to sources of interference. So that includes like metal. Yeah, basically metal is sort of the big thing. If the concrete has a bunch of rebar, that could be another source of interference as well. So in general, what we recommend is that you place the ECU in a way that's less prone to what's called to interference. And if necessary, if the ECU is not able to move, you can use an antenna as a way to extend, as a way to have have another location for the microinverters to talk to. And normally, I would say that if you have a multi-story residential home, it's generally okay from a microinverter communication perspective. But if you have a larger commercial where the roof is like really high and it's harder to reach those microinverters, then you may want to think about putting the ECU either on a roof or having an antenna extending out. Another thing also as well is to be cognizant with regards to nearby devices, because the Zigbee wireless protocol, it's on 2.4 gigahertz, which is the same band as Wi-Fi. So in general, it's good to make sure that the routers, that any sort of like Wi-Fi routers are not super close to the ECU. Ideally, there's a little bit of difference. If it's not like directly next to each other, it's okay. But as long as like there is a healthy distance, like a couple of inches or couple inches or like a feet apart from the routers, then it will be able to be less susceptible to interference. And a final note also is it's better to put the ECU in the middle of an array as opposed to the edge, because as mentioned earlier, the microinverters, they act as Zigbee relay points. So microinverters can pass down data along to the nearby microinverter, and then pass it to the ECU through that way. But then if you have it in a situation where like these 8 microinverters are trying to serve all of these microinverters, that will greatly bottleneck the data transmission between the ECU and the microinverters. So in general, it's better to have it's better, not ideal, but it's better to have the ECU here where it sees more microinverters, and then these inverters can be passed along through this array. But of course, the better, most optimal way is to put it in the center so that it reaches more microinverters that way. As mentioned before, it's possible for data to be passed and to be leapfrogging off of other microinverters, but ideally we try to limit that so it doesn't bottleneck the data as much. All right. So that was definitely a lot of information with regards to ECU placement recommendations. I'll pause here briefly for any questions, but if not, I'll talk a little bit about what are some techniques that we can do to improve communications between the ECU and the microinverters.
Any folks, any questions out there, folks? Okay, I think we're still good. We got a knowledgeable bunch.
Great, cool. All right, so I will move on to how to improve Zigbee communications. So one is that you can basically make the Zigbee scream louder by adding a signal booster. This is the part number that we have. So if you need to have something that makes a Zigbee boost, this is the way to do it. And this is one methodology of doing that. It's a powered antenna, and it's basically relaying the signal through the antenna through here to be able to reach more microinverters. Another one also, as mentioned earlier, is to use a antenna to basically boost the length. Main thing is to make sure that the antenna is not super long, because if it's too long, then it'll be tough. It'll be easier, or the signal dissipation will be a lot, or how to say, the signal will be dissipated a lot longer if the length is too long. So if you were to do something like this and have the antenna closer to the microinverters, then that will extend the range as well. Similarly, if you have a scenario where there's like a metal box, you can make sure that you have the Zigbee antenna on the other side of the metal surface so that you'll be able to reach the microinverters through this way. Here's another example of putting ECU inside of a box. This one I have here is the ECU-R. So that's something that you can do to put the microinverters onto the roof to get a little bit closer. Some other tactics as well is, as mentioned earlier, the ECU needs to talk to the internet. And so I'll talk a little bit about ECU internet connection communications. So as mentioned earlier, these are the two options. One is with an Ethernet cable. Ethernet cable is definitely the has a more reliable option because it's like a hardwired connection to a router. But it's possible to do Wi-Fi. And in general, in terms of setup, we generally recommend connecting the ECU to Ethernet first, basically just to get its firmware to be updated first. And then once the update has been completed, you can then move it into Wi-Fi. But it is possible to do Wi-Fi connections for the ECUs. But with the general nature of ECU Wi-Fi connections, it's tough when it's from a range perspective. So if you are trying to get additional connections, there's additional ways to extend the range. If you're doing Wi-Fi, some ways to extend is by using like a Wi-Fi extender or like a TP-Link type device, where the ECU will connect to the extender, and the extender connects to the Wi-Fi router, so it kind of hops. We've also seen power line adapters where you plug the where it communicates signal through Wi-Fi through like a power line, and you connect that to the Wi-Fi. That's another option as well. Similar to the Zigbee booster, you can also do a Wi-Fi booster as well, and that's another option for communication. Another option that we also have is a
We did
sort
have
of
a
a
couple
USB
of
dongle.
questions, Chris, actually.
Oh, yes.
Sorry. Oh, I see. Are you actually writing back to some of these? No. Okay. What's the temperature limitation of the ECU?
Oh, I don't have it offhand. It's on the data sheet. I can pull it at the end of the meeting to see if I can get that information. But that being said, you are correct that there is a temperature rating for for the ECUR. Actually, I just pulled it up just now. It's going to be -20 to +65 degrees Celsius.
Great.
Yeah, I
And
did
then
Fahrenheit, so you guys use Celsius.
also not a question, but a comment, good info about improving comms. This is often a challenge, so I'll take the best practices to the team.
Absolutely. We also recently just created a white paper on Zigbee communication. So kind of everything I'm describing right now in a PDF format. We're going to make it publicly released pretty soon. But if I can get maybe the email of the person, I can send over that document. Cause so you can get a sneak preview as to
For
what it
sure.
looks like. Okay.
Sounds good.
Yeah, maybe Matthew, I can follow up with you afterwards.
Mhm.
Yeah, any other questions?
Oh, that's it for now. Thank you.
Great, thanks, Matthew. All right. Another thing that we also can recommend as well is by using a cellular dongle. So this is something that's sold by APsystems, and this is something that you would plug into the ECU, a USB port, and then you would need to get a SIM card and to plug into this dongle. In general, I recommend getting a pre-activated SIM card. I don't know what options are in Canada, but in the United States, there's a company called One NCE that you can purchase a pre-activated SIM card, and it's pretty affordable with regards to the data that you can use. And if you use that and plug it into the SIM card for the dongle, and then plug the dongle into the ECU, that will allow you to have a cellular connection. And this might be the preferable option if you don't want to piggyback off of the Wi-Fi network of your customer. In terms of sizing the data, this is what I generally would recommend. So for every microinverter, it's going to be 150 kilobytes a day. For an ECU, it's going to be 2 megabytes for a day, and you can use that to sort of extrapolate how much data you would need for a system here. I've done a quick example in terms of like the cost of a plan. This is one where I have a 50 QT2 site with one ECU, and for 10 years I kind of estimated into this, and this is with how to say a SIM card that I had found in the States. So I use USD in this example over here. But yeah, in any case, that's sort of my main section on communications. I'll pause here if there's any further questions regarding communications. Otherwise, I'll move over to commissioning process.
We're good for now. Thank you.
All right, cool. All right, let's move on. All right. So first, I'll talk a little bit about commissioning overview. So the important thing to do from a commissioning standpoint, I would say, is there are 3 important tasks that need to happen from a commissioning standpoint. One is connecting the ECU to the internet. 2 is associating the ECU with the microinverters. And 3, creating an account for the customers. So for each of these 3 steps, one of them has to be done on site, which is connecting to the internet. Both of the other 2 items, account creation and inverter association, that can be done either on site or on premise. So I will sort of go over some 3 options that you can do when you are commissioning a system. So this is the on-site office option. So basically, the first step is to create an account on the email portal, but you only do the first 2 steps. Then the second step is once you go on site, you set up the ECU and connect it to the internet, associate and scan the microinverters to the ECU, and then you sync them. Once that is done, you can go back to the office and then complete the installation afterwards. So that's option number 1. Option number 2 is on-site and then off-site. This is a full on-site procedure. So the way you would do it is by connecting the ECU to the network, and then just setting up the microinverters that way. And then you can go onto the email manager app, log into your app, and set up the account in there. So that's the full on-site option. I personally don't really like using this one. I'd rather, because I feel like the office is a lot easier to go through the account creation because there's a lot of fields that you should enter. And I don't know, I hate typing with my thumbs. And then the other option is to do everything on site first and then do off site afterwards. So the way you would do it is that once you go on site, you set up the ECU, program and associate the inverters to the ECU. And then afterwards, you go back to the office and do the account creation afterwards. So to me, I personally prefer the third option. Our tech support agents prefer the first option. Um, but yeah, the main thing is that I would say if you have to do something on the site, the most important thing is to connect it to the internet. Um, I would recommend connecting the microinverters to the ECU on site also because you'll be able to know immediately if a system is working or not. So I'll talk a little bit about how to do that. So on the email manager app, that's basically the same app that you use to set up the microinverters for the DS3s. Same thing, same app you would use for the QT2s. So in general, what I recommend, I think this is also helpful for residential installs. I recommend taking 3 screenshots before you leave the site after you scan the microinverters. The first screenshot is the homepage because that shows you and proves that the internet is connected connected to the system. The second image is the module page because the module page shows you if there's any particular microinverters that are not producing, so you immediately know to go back up to check if there's like something loose or if there's truly a panel that's connected there. And the other one is inverter connection progress, because this page tells you the status of whether a microinverter has a healthy communication with Zigbee. And if you confirm that, then you know that you're going to be good from that perspective. All right. So, any particular questions regarding the EMA Manager app? The next topic I'll be talking a little bit next is going to be the web portal.
No further questions at the moment.
All right, cool. Sounds good. Okay, great. So this is the email web portal. So instead of the app, this is the web portal that you can look at all the information on your website. And it's really helpful to be able to do some initial debugging before you go on site to see where there could be some issues. So I'm not going to do a full overview of the portal. What I want to sort of leave here today is going to be giving a couple of debugging tips that you can go onto the email portal to just take a look and see what could be the issue before going on site. So here's some debugging tips. First of all is this is the first thing that I always take a look at to see if an ECU has talked to the internet is just by looking at the heartbeat time. So if you go to the site, go to the customer page, diagnose, I think it's diagnosed afterwards. You'll be able to see a timestamp, and that timestamp will let you know if the ECU has ever talked to the internet. If it's been a while, then you'll see that this heartbeat is a couple days or months old, and that will let you know the last time it's talked to the internet. I would say that the heartbeat it's probably like every 15 minutes, every 10 minutes that I've seen it get updated. So I would personally get worried if I don't see the heartbeat within like an hour or something along those lines. So this is one thing to just quickly see if we're getting any issues with the internet. Something that's also powerful as well. Oh, I wish I showed this how to get this page. But if you go to the module page and then you select the inverter that you want to do a deep dive into, you'll be able to see the AC and DC side information for the microinverter itself. So for this example over here, you notice that the AC voltage is 120 volts. And then down here it goes to 0 and it goes to 240 up here. So actually what happened in this example over here was that the electrician had mixed up, this is for a split phase 240 system. The electrician had actually swapped line 1 and neutral. So instead of putting 240 onto the micros, they put 120 onto the AC output of the micros instead, which led to the system not working because it expects 240, right? So after they have swapped it here, then that's when we were able to confirm that the system is up or down. Similarly, if you notice that there's a lot of microinverters that had 0 volts on the AC, it's going to be good to check to see if there's something weird on whether there's a breaker issue, whether there's a home run issue, a wiring issue on the AC for that particular branch. That can be another thing that'll be helpful to identify where to look to debug systems. Now on the DC side, this will also let you know to see if the voltage and currents are expected. So in this example over here, we see that power is 0, current is 0, which is not a good sign because it's not producing. But you see that voltage is currently 11 volts. Normally panels, since it's a single panel, they should be like 30, 40, or something along those lines. Basically, it needs to be the VMP voltage. But in this example over here, the voltage is lower at 11 volts. So actually, as a fun tidbit, if there is an empty channel, so there's no panel connected to that channel, the floating voltage is typically like 9, 10, 11 volts. So in this example over here, we actually have a panel that is there's a panel that's not connected to this particular inverter. And they went back to look at the system, and it was indeed intentional for that channel to be disconnected. So that was good that we were able to verify that as well. Another important thing to check as well is to see if the grid profile has been selected correctly. And that can be done locally or can be done remotely. If you hit the grid profile and then check the grid profile that's selected, that's another thing that we can check as well to make sure that the correct grid profile for the region has been selected correctly. One thing I will also mention is that it's a common problem that we've seen where the grid AC voltage or frequency fluctuates out of bands because the grid profile tells the microinverter that only produce power if you see a voltage between a certain range. And we've seen some scenarios where if the grid is unstable, that the voltage goes higher than what the microinverter thinks that expects. So in those scenarios, what needs to happen is that the AC parameters need to be adjusted. Right now, if you give a call to our technical support agents, we'll be able to resolve it really quickly. But we are looking into how to allow installers to be able to set those AC parameters. As for example, there's one utility that demands UL 1741 SB parameters, but in reality, though their grid is a lot more unstable and their AC voltage is higher than the default values for 1741 SB. So we've found sometimes we had to change the AC parameters to expand those. So one thing we are looking at is there's a way to give installers the ability to adjust AC parameters, and that's an open topic that we have right now. But in any case, that's something that to be in consideration of with regards to AC voltages. Okay. All right. Any questions regarding the debugging tips? Otherwise, the next thing I'm going to be talking a little bit about next is if we run into a scenario where there's only one panel that's functional, and how to debug and how to address those issues.
Everyone's good at the moment.
All right, cool. Let's move on. By nature of multi-module microinverters, it is possible for a panel to go down, and it's often hard to determine if it's a panel issue or if it's a microinverter issue. So the process that I'm going to describe is called a DC lead swap. What that basically does is that it confirms whether the issue is with the inverter or if it's with the panel or the wiring. So what we say is that you basically take a functioning panel and you swap the channel of a non-functioning panel. And if the problem moves like in this format here, then that means it's an inverter issue, and it can give us a call to make sure that is a problem, so that you can get a replacement unit. If the problem does move, that means that it's an external issue, and so it's either something with the wiring or the panel that's causing the problem. So here's a more graphical view. So in this example over here, I have a panel or wiring that has issues, and that's the red one over here. According to EMA, we see that the voltage is looking strange, but the other panel is looking good. So if we swap the panel like this, oh, I didn't know it was animated. Great. Then if you see that the problem has traveled, then that means you know it's the panel or the wiring that causes the issue. But say, for example, you have a scenario where the actual channel of the inverter is having a problem, and after you swap, the voltage changes, or the voltage does not change. That means that it's something up with the inverter. And then in that case, we would be able to issue a replacement unit. So in terms of recommendation on how to deal with this process, first off, we generally recommend bringing in an extra inverter and some extra DC extensions in case the swapping is a little bit hard to do on site. Turn off AC, perform the swap, turn AC back on, mark when the time was swapped, and then take a look at the EMA portal. If you see that the wattage of the panel of the channel had changed, then you'll need to take a look externally to see what could be the issue. But if the channel did not change, give a call to our tech support agent. Let us know what the ECU ID is, the time that you swapped the channel, and the inverter ID. They'll probably ask for additional pictures to show the swapping event. And if the problem did not move, we'll issue a RMA, and then you can go ahead and swap the inverter that you brought extra, so you don't have to go back and forth for the system.
We do have a question here. Any suggestions for the inverter NC troubleshooting?
Yeah, so for inverter NCs, the reasons are usually from poor Zigbee communication. And for those, I would refer to the earlier slides where I was talking about ECU placements, antenna placement, boosting the signal, so on and so forth. And as mentioned earlier, we have a PDF of a white paper explaining how to improve Zigbee communications that we will be releasing shortly. So we'll be doing like a what's it, newsletter or like mass communication or announcement that this white paper is out.
Great.
Yeah, thank you for the question. Okay. All right. So that's the end of my presentation. The next slides is basically like simple things like how to start. So as mentioned earlier, we have installation training webinars that we held monthly. Our videos are also on YouTube as well. And I guess you guys went through this training, so that's already pretty good as well. Register for your email account if you haven't yet already. It takes a little bit of time to process those accounts, so I recommend doing that soon. The learning resources, we have a FAQ page, training page, product documentation page, the registration page, and the support page all on here. We have a really nice YouTube channel that explains that has a lot of videos that are released, excuse me. And then also most importantly, this is our tech support number. For any sort of urgent calls, this is the number that you would give a call to. We have a dedicated Canada line, but sometimes it overflows to our American tech support line as well. So it should be pretty well staffed. And these are also our hours as well. 8 a.m. EST to 5 p.m. PST, Monday through Fridays. And yep, that's all the information I have for today. So I think I'll leave it there. Is there any particular further questions for me? I think now's a good time to open it up. But otherwise, yeah, thank you very much. Thank you very much, everyone, for listening into the presentation.
Any questions out there, folks? Okay, I'm not seeing any. So thank you, Chris. Thank you, APS. Really appreciate you taking the time to help educate us and our customers on this product. Thank you, customers out there, for attending. Just a reminder, this was recorded, so it will come out in the next newsletter. It'll also be shared on our YouTube channel as discussed. If you're not on there yet, please sign up. You'll see this webinar as well as all of our other webinars that we've done. And once again, if you haven't signed up for the web shop, please do. You can go in, you can see all the APS spec sheets, install manuals, pricing, inventory, things of that nature. Once again, thank you everybody, and hope you have a great rest of your day.